Welcome to the i-ROM Modelbuilder tutorial. The Model Builder is a quantum leap in the design of sensors and actuators. Easy to use, for fast and accurate results and perfect for optimization. In this video we'll give you a short introduction how to build a single-axis accelerometer model in the i-ROM Modelbuilder. In the last video, the anchors have been already placed. Therefore, in this video we are going to build the seismic mass, the springs and the comb cells. To build a seismic mass, we can use three different methods. The first method is to use 5 separate rectangles, which will be automatically connected if they touch. The second method is to use one big rectangular block and subtract the other rectangles. The third option is to use a polygon where we define all geometry points which can form an arbitrary shape. Any method is suitable in the model builder. For now, we just use the polygon method. In the model file, the body parameters are already defined, and we can place the poly command. Here the body is added, the body ID is assigned to 1, and the material number is set to 1. The layer is the default layer, and does not need to be defined. Then the x1 and y1 coordinate of the first geometry point is declared. For better visuals, 3 dots declare a new line, and after that, a comment is placed, which indicates the key point number. In the model builder we can now press build and we see that a mass body is created. As a next step, springs are placed. Springs are defined between spring location points called S-lock. Each S-lock has an individual ID and can be placed either on the mass body or in an open area. In this example we are going to place the first set of S-locks. 1, 2, 3, 4, and 5. S-lock 5 will represent a loose end, which is here called connecting bar. We place the S-lock commands and press build solid. To see the points, we can turn on the S-lock indicator and number on the side panel. With the spring command we now connect the S-locks, and the springs are automatically created. Furthermore, with the spring command, different width and shapes could be defined, but here we just want a bar spring with a constant width. In the model builder we can check if everything is properly connected and then we repeat the process for the right bottom part. There we define the next set of S-locks, and then we place the spring command. Additionally, we now need to connect the top and bottom connecting bar, and in the model builder we can see that everything is properly connected. This process is repeated for the left side and the accelerometer looks almost finished. For details, we will place 4 stoppers on the mass body in the direction of the anchors. They are defined through the stop command. The shape of the stopper is circular, comes the body ID, the material ID, the x and y of the circular center point, and the x and y of the fixed target node, which is here the surface of the anchor. The final value represents the radius of the stopper, which is here 4 micrometers. In the model builder we can see that 4 half cylinders are created on the mass body. The next steps creates the comb cells. They are defined through the comb command, which has the following setup. At first a labeled is set, which is here called sense plus, and then finger combs are defined through the area indicator. Then the number of fingers, the finger width, the finger length, the anchor block width of the fixed part, the required travel range, and the electrode gap are assigned. Back to the model builder we build the solids. As we can see, the comb cells are correctly connected to the mass body. Now, we add rectangular patterns to consider perforation holes. Last but not least, master nodes are placed to read the simulation results on these nodes. Over the side panel, the nodes can be visualized in the model. To perform a simulation, build ROM is pressed, and then we can perform a modal analysis. There we define the scale of the motion and we can see that the mass body is actually moving. In the next videos, we will cover the 4 analysis types for this model, which will include the basics in modal, static, harmonic, and transient analysis. We hope to see you there as well.